Hi everyone, welcome back to AI Lit Review. Today I want to talk about a paper I was personally obsessed with for a long time, measuring the intrinsic dimension of objective landscapes. It's an older paper, but it quietly shaped how we think about why deep learning works, added up to the long line of work of intrinsic dimension, and even inspired ideas like low rank adaptation years later. First, I would like to point out that this paper is not about dataset intrinsic dimension. When people usually talk about intrinsic dimension, they mean dataset intrinsic dimension, which means how many coordinates you need to represent the dataset X without losing information. So, it means it is about dataset difficulty, how many number of coordinates you need to represent the data. This paper is completely different. It is not about dataset difficulty, it's rather about model difficulty, or more precisely, the difficulty of the objective landscape. In supervised learning, we don't model P of X, given that X is a dataset. Rather, we optimize conditional probability distribution of Y given X, which means we're solving an optimization problem over model parameters. So the probability precisely should be p theta y given x. The paper shifts perspective. Forget about the data manifold. Look at the loss surface over parameters. That surface is called the objective landscape. And what this paper is trying to explain is how many number of parameters are needed when we're trying to optimize in this objective landscape. So let's go through briefly about objective landscape before diving into intrinsic dimension. Imagine a very simple case, a linear regression model with two parameters, W1 and W2. And imagine W1 as x-axis, W2 as y-axis, and loss value as z-axis. And every point, any particular number value, W1, W2 gives you a height, the loss value at that particular point of particular point of weight value. That's an objective landscape, as you can see in the right part of the slide. And gradient descent is done on this landscape, trying to find the minimal loss point known as global minima. Now scale this idea up. Instead of having just two parameters, we have millions or billions of parameters. And loss space or loss surface living in unimaginably high dimensions. Yet gradient descent in this high dimension somehow finds good solution, and that is already suspicious. So this paper is trying to explain how the gradient descent in this high dimensional space works. So the core question is, do we really need to optimize in all those high dimensions? Or put differently, is the true difficulty of the problem much lower than the number of parameters suggests? If yes, then the landscape has a low intrinsic dimension. So, what intrinsic dimension means here is the minimum number of independent directions in parameter space required to reach near optimal performance. So, if a model has 10 million parameters but only needs 5,000 directions to solve the task, to solve the optimization problem, then the intrinsic dimension is up to 5,000. And let's see how the paper measures the intrinsic dimension. They first freeze the full parameter space. Instead of learning the full weight vector W, they do this. 1. Sample a random low-dimensional subspace of dimension d, small d, which is a lot less smaller than the big D, the size of the full parameter space. 2. Define a fixed random projection matrix P. This matrix is not learnable and it is used to map between the small subspace of dimension theta d towards the big theta d. That is the original parameter space. And we learn parameters only in the low dimensional space, so we only learn theta small d. and map back to full parameters via the following equation. So forward pass uses full model, but backpropagation updates only theta d, so that optimization happens entirely inside a low-dimensional slice of the objective landscape. As you can see in the figure, there is a two-dimensional slice inside the three-dimension. This is a really simple case, but the slice that you see in the d equals 3 part of the figure is how you actually optimize or backpropagate using smaller dimension 2 in the actual three-dimensional space. But the real dimension is really higher than this, and the small d, the subspace, starts with d equals 1, 2, 3, and it increments, it becomes 10, 100,000, and at each d, they train and check the performance. If the model reaches 90% of the original full training performance, they stop, and that d is declared the intrinsic dimension. This is quite brute force and inefficient if you think about the actual search of the D. But the existence of such a small d is the discovery. So let's see what they found. They found out that models can reach near full performance using orders of magnitude fewer parameters. So if you look at the figure, the C410, let's see. In Linnet, you have number of parameters of 62k, but intrinsic dimension is 2900, which is order of magnitude smaller than the number of parameters. And they also found out that different tasks have different intrinsic dimensions. For example, Atari Pong has an intrinsic dimension of 6000, which is compared to the C410 2900 or 2900 is slightly higher. So we can assume that Atari Pong is slightly a difficult problem than C410 dataset classification. And intrinsic dimension becomes a measure of problem difficulty. Let's explain why this paper matters. This paper established something fundamental. Successful deep learning does not require searching full parameter space. The solution lives on a low-dimensional manifold embedded inside a huge space. One sentence for you to take away is deep learning problems look high-dimensional, but their solutions live in surprisingly small spaces. And that's the intrinsic dimension of objective landscape. Thank you for listening.